for unless you live underneath a rock, there's no reason why you probably are not familiar with Marshall besides being here on campus and the faculty in geography. He has done what I think is an important for all of us to figure out how to do, and that is really bring our science into the hands of the public in a lot of his work, and along with his academic credentials, and we'll forgive you for being a 3-time graduate from Florida State.
Go Knowles.
Be forgiven, but
that's good to know. That's
and former president of the American Meteorological Society. Marshall also hosts Weather Geeks on Sundays, Sunday at noon at the Weather Channel, writes a column for Forbes, and spends a lot of time communicating these important, especially now, important of climate science and climate change to a most confused public.
That's a nice way to put it.
I don't know what else to say. So I'm going to let Marshall talk to us about extreme events, climate change, and the energy from water nexus. Thanks, Marshall.
Thanks, Liz, for the invite and everyone else involved in the invite. Yeah, I'll try to anchor as close to right here as possible. Can everyone hear me and see me okay? May wander around a little bit. It is an honor to be here. I hope to check some of the future seminars in this series. They look very interesting, so I'll definitely be back over myself. It looks like part of my slides are being flipped off at the bottom because it does have my coordinates. You can see some of the things that I'm up to. There's also down here at the bottom, it says Forbes contributor, and I also have my Twitter account. If you're on Twitter, you can follow me at Dr. Shepard 2013. So this talk actually, boy, when I first was asked to give this talk, I was like, okay, how am I going to frame that talk? Because I'm doing a lot of different things related to the topical matter in the seminar series, but I actually don't necessarily have a talk of this nature. Usually when I accept the offer to talk, I'm like, oh, sure, because I know I already have kind of a talk in place. But this one I had to kind of think about and pull together some things to bring together a coherent story that fit the theme. But it wasn't a stretch because, as I said, I am doing things in these areas, my students and I, but bringing them together in a broader sense was a bit of a thought. So that's my topic. Yeah, it really is getting cut off badly, so I'll try to read as much as I can that you're missing. Yeah, is it something that I can resize on my end? Because it looks fine on my computer. Let's see if I can just quickly go out and system preferences. Yeah, I think it's kind of automatically setting in my computer.
You could present it like that.
Prefer not to because I've got some things I want to do.
Jeff, we're the guy that helps set it up. Travis.
I mean, if not, we can just kind of make it work.
You can also make sure it's mirroring the screen, the settings.
Yeah, because I'm just connected wirelessly. I'm not actually connected.
Oh, you're not connected.
No, that's what I was intending to do, but they were using Zoom. So. But
There you go.
Oh, there it is.
We got it.
He did it.
I didn't know what I did before.
You got made it full screen.
I just went out and went in again.
Okay, perfect.
All right, so that works. So yeah, now you can see everything. So I knew that was going to be a problem going forward. Just so glad you were able to get that fixed. So now you can see all of my school coordinates. I recently became the associate department head of geography. I'm not sure that's anything to put up there. But so just to kind of give you some motivation for some of our recent work on food and climate, kind of setting the stage. 50% increase in global food demand is expected by 2030, 30% increase in water demand, 40% increase in energy demand. And many of you probably know this to be a part of this whole notion of the energy food water nexus. And that's really the motivation. And the drivers associated with these increases are population for the most part and urbanization. If you look at many of the least developed nations of the world, you're seeing increasing urbanization as well as increasing population. So 2015 paper talked about that many frameworks that talk about this energy, water, food nexus typically focus more on things like greenhouse gases, land use, resource management efficiency, and societal facets, but have paid little attention to the hydroclimate aspects. And so if you are savvy at writing proposals, you can probably see that this was probably one of the leading justifications in my recent NASA proposal for why they needed to fund it. Because no one had really talked about this EWF-N from the perspective of the hydroclimate, which I'll define in a moment. So this is a figure that really frames that. So when we talk about the availability of food, what are the challenges? If we kind of assume agricultural production as sort of a central hub, and then you sort of add to that these forcing functions of growing population, falling poverty, this drives increasing demand, particularly for food. Additionally, you've got technology, market forces, land cultivation, rainfall, rising temperatures, increasing consumption. These are all sort of central players leading to this agricultural productivity in response to demand. Now, where I come in, because I'm a climate scientist, I'm actually an atmospheric scientist. I actually do more meteorological research than climate, but I do climate too. Climate change is clearly a stressor or a forcing function on availability of food. Yet, if you look at many of the frameworks that talk about the energy, water, food nexus, as I established earlier, and as the literature establishes, that aspect of the problem is somewhat understudied. And so that's what got me interested in this challenge. So if you look at this particular graphic, this is one of the graphics that I used in my proposal. Talks about sort of the linkages between climate, water, energy, and food. And if you just kind of digest it for a second, you can see how climate, in some regard, it's not because I'm a climatologist that I put climate at the top. It's that climate is really a driver in many senses of the water supply that we see around the globe, the energy associated with exchanges related to climate, and so forth. So I guess the point I'm really making is to really have an informed discussion about the energy, water, food nexus. You have to have an informed discussion about climate. And so that's what we've been trying to do in some of our research. So as a part of the hydroclimate, you've seen me talk about hydroclimate. What do I mean by hydroclimate? Climate that essentially involves aspects of water, right? So when I say the word hydroclimate, you can think precipitation, clouds, soil moisture, the hydrological cycles of climate, right? The hydrological components of climate. And in my case, I'm usually most interested in rainfall. If you go back and look at my portfolio of peer-reviewed publications and grants and whatnot, somewhere in there you're going to find rainfall usually, whether it's how urbanization affects rainfall or how tropical cyclones are changing rainfall production or how rainfall is affecting agricultural. Usually the central theme of my research, no matter what it is, usually involves rainfall. So, I spent 12 years at NASA Goddard Space Flight Center before coming to UGA. I was the deputy project scientist for a satellite mission that now is in orbit called the Global Precipitation Mission, GPM. So rainfall is my thing. So when we talk about hydroclimate extremes, yes, drought is one, sort of the deficit of hydro, if you will. So it certainly falls within the scope of hydroclimate extremes. We've seen recent examples. This is actually a picture I used in one of my Forbes articles. I talked about the Gatlinburg wildfires and talked about some of the sort of meteorological, short-term climate, and possibly climate change linkages to the wildfires that we saw this year. So that's out there in Florida. So we have seen examples, even as recently as the last fall, we're kind of coming a little bit out of it now, of drought in the Southeast. And we know that drought in the Southeast can be a particularly negative influence on agricultural productivity and agricultural activity in this state. If we go back to 2012, this is an example that I often use. This is from CNBC. This is January 2013. If you recall back 2012, there was a significant drought in the middle part of the country, the breadbasket of the U.S. It was so bad that barges couldn't get down the Mississippi River. The water levels were so low that they were getting stuck. Now, there is a lot of grain that moves up and down the Mississippi River. And so the point I'm making here is that we saw significant food price spikes in relationship to that 2012 drought. And again, you can see it here reflected in another way. Two industry and waterway groups estimate that low water in the Mississippi shipping channels resulted in these commodity losses over the period December to January. We're talking billions of dollars. So, I mean, from my lens, we shouldn't have any problem making the case to politicians and the stakeholders, right? When you throw billions of dollars around, their little ears perk up. So, you know, and as Liz is talking about, look, I mean, I've briefed the White House and I talk to people at the Waffle House. So, I mean, you got to have different messages when you're communicating this. So, the message that I'm giving you about this will be different than the message I give when I go to the White House or Congress, or if I'm talking to some Rotary Club member at the Waffle House. And so, as an aside, we have to be very strategic going forward in how we communicate this science. And so you'll see, I mean, I can write the peer review papers and go to the AMS conference and talk all the science stuff, but increasingly, and this is a challenge to all of us in the room, we have to think a bit more strategically and from a more savvy point of view in how we communicate our messaging. So that's always something very prevalent in my discussions. All right, so with all of this going on, let's talk about climate change a little bit, set a little context for this whole notion of hydroclimate change and extremes. And then we'll come back to sort of the implications for food. This is a very effective graph, I think, that shows the changes in global temperatures from 1850 to 2016. Now, clearly, there are not as much data in the earlier parts of those graphics. So you have to kind of understand that and take that with a grain of salt. But the kind of key point is this, the reason I think this graphic is effective is your eye sees a lot of red in these latter years, right? Which suggests that our planet is warming. Yes, there's natural variability. Yes, there's a natural climate change that occurs due to various things that I'll talk about momentarily. But in recent decades, the rate of change of warming is what climatologists are concerned about. If you kind of rewind your mind back to high school in your calculus class, when you learned about derivatives, right? It's the rate of change. That's what a derivative is. It's the rate of change in recent decades that is what we as climate scientists always think about. Because we can quibble about one year being warmer than another year, and yeah, there's variability. But if you look at the rate of change, that's what we focus on, right? Because a lot of these changes are occurring on the span of years to decades. In some cases, natural variability took several hundreds of years, those kinds of changes. So signs of climate change are all around. I mean, this is sort of the litany of things you hear about: greenhouse gases, sea level rise, ice sheets, global temperatures increasing. And these things impact people, ecosystems, and the economy. They do. So part of what I'm going to talk to you about related to extremes is how we can, or can we, link some of the extreme events that we're now seeing to climate change. And I was one of the authors of the National Academy of Sciences report issued last year on something called attribution. Can we attribute extreme events in current context to climate change? So that's going to be a central theme of this talk, and then I'll certainly couple it and bring it back to food. So let's just look at one example of that sort of geophysical system change, because I think it's compelling. Now, let me stop this first. What you're seeing here in white is sort of short-term sea ice, and then, white is long-term perennial sea ice, and then the sort of grayish is sort of one-year sea ice. And this is over the period satellite era, 1984. This is some data from NASA. It's going to come through the present. So here we're counting down from the years here. And just watch the change. I mean, you don't need me to say anything, just watch it. You see the seasonal, yearly ice, ebb and flow. We're in 1993 now. 95, 96, 97. You know, we're getting into a period where the warming really is starting to ramp up, 99, 2000. You notice the perennial, the white is the long-term ice that should always stay there. You notice it's pretty much the white, how it just is almost gone? Yeah. Why this is a concern for many reasons. I was on another National Academies panel about 5 or 6 years ago. The Navy pulled together on national security issues. They're really concerned about this because you're opening up another threat lane, if you will. But believe it or not, one of the biggest things they're worried about up there is freshening of the ocean, because their sonar is tuned to certain assumptions about how salty the water in the ocean is. The Navy's really concerned with that. Who knew? That was one of the things that popped out of it. But what's really important about this is look at where the most significant warming is. It's in the polar regions. Now we can link that to this, because what we know is that when you have all that ice up there, that bright white ice and snow, it's reflecting the sun's energy and moderating the climate. But as soon as you start melting it and opening up water, that water heat can be absorbed and you have a positive feedback and you get more warming. And so that's why the Arctic region warms more. All right, well, how does that relate? No, there's no chalkboard in here. Is this a white?
Yeah, you did.
How does that relate to, draw a picture of the U.S.? I always like to think this looks like a dinosaur or Barney or something. This is the U.S. How does that relate to our weather and extremes? Well, there's something called Arctic amplification. And this is a theory that has been put forth by Jennifer Francis and Steve Babris in a paper several years ago. Right? Oh yeah, you might not be able to catch some of the video. And the notion is that as we melt more ice in the Arctic, it is affecting our weather here in the U.S. How? All right, well, I need a visual example. What's your name? Casey. Casey, what if I gave you a rope and we played tug of war with that rope and you and I were pulling it? What would the rope be? If we both were pulling with our strength, how would the rope look? It would look straight, right? We're both exerting force, and it's a straight force. Well, in meteorology, you all have heard of the jet stream, right? The jet stream is a pattern. It comes into our United States, and it separates net colder air on the northern side of the jet from warm. And that jet stream meanders and flows. When you see a dip in the jet stream, that's cold. When you see a bump in the jet stream, that's usually associated with warm. California, for the last several years, had been under a pattern of warm, a ridge. That's why they've been under drought. Now, the thought process is when we melt more ice, right? So,
a lot of those, I don't want I like.
Good. Sorry.
it's okay. Hold your thought. Remember our tug of war example. All right. So the thought process is that when we have a regular polar equator gradient, in other words, it's cold in the poles and warm in the tropics, you have a strong gradient of temperature. A strong gradient of temperature means we have a strong jet stream that just blows through. But when we weaken that gradient, and guess how the gradient gets weakened? When the polar region is melting. There's no longer a strong gradient. So we no longer have that strong pull. If one of us releases our grip a little bit on the rope, what happens to the rope? It sags. It's more wavy. So when we reduce the gradient in temperature, because the polar region is warming, so we don't have as much of a difference between the tropics and the poles, we have a saggier jet stream, which means larger waves, which means bigger droughts, or bigger systems that produce floods. So that's the concept of Arctic amplification. So read all about it. So what I just did there is kind of sort of eroded this notion that that's about polar bears. I like polar bears, but there's a bigger reason that's of concern, because what's happening up there is linked to our weather through very basic meteorology of waves, Rossby waves. That's what governs our weather patterns. But yet, I still get this question a lot. I'm a meteorologist by degree. I have 3 degrees in physical meteorology. People say, well, you know, usually people find out I'm a meteorologist, they ask me, what's the weather going to be tomorrow? I don't know, because I don't really follow day-to-day weather. I'm a research meteorologist. So they ask me what channel I'm on. I'm not. Well, I have a show on the Weather Channel, but I don't stand here and do this every day. They'll ask me, you know, is their cousin's wedding down in September outside going to have rain? I'll follow that. I probably can't tell you anyhow. And more recently, they say, well, do you believe in climate change? Now, as an aside, before I move on, to me, that's like saying, do you believe if you jump from the top of that building, you're going to fall? Because gravity does exist, right? Science is science. It's not a belief system. And I also get this one this time of year when it gets cold. Oh, it's snowing outside, or I'll get a tweet, hey, Dr. Shepard, I got 40 inches of global warming in my yard right now. What are you guys talking about? But that's really like saying, hey, this ship can't be sinking because my end just rose 200 feet. So, you know, I'll talk a little bit at the end of the talk about the narrative that we're dealing with. But the science, at least the best science that we have, suggests that our planet is warming and there's a human contribution. So now let's get into a little science 101 here before we move forward. Climate variability definitely includes natural processes. I'm amazed as someone that just established that I have some pretty decent credentials in the field of atmospheric sciences, yet I'll be in Walmart and someone will come up to me and they find out what I do and they go, well, you guys know climate change is natural. I was like, yes, I do. I promise you I didn't miss that in my various degree programs. So we know that there are ice ages, Pacific decadal oscillations, El Niños, sunspots. These are all natural things that affect our climate system. No doubt about it. But let's look at this. Last 400,000 years up to 1850, which is the Industrial Revolution. Do we see some interesting things from ice core analysis? Atmospheric CO2 and temperatures kind of do the same thing over the last 400,000 years. But CO2 never really got above about 300 parts per million. It's kind of capped. It was limited over the last 400,000 years or so. Until we got outside of that natural range during the Industrial Revolution. So now I think we're now close to 402 parts per million. We're in a plus 400 ppm world, and for the time being aren't headed back. So yes, the climate change is natural. And by the way, what we're seeing here is just the well-known Milankovitch cycles, right? The notion that every 100,000 years or so, the shape of the orbit around the sun changes, right? We've known about Milankovitch cycles for quite a long time, or it wobbles a little bit of the tilt of the Earth's axis changes. So these sort of natural, so I just proved to that person at Walmart that I know that the climate changes naturally, and still does. Except now it has a human steroid on top of the natural change. I'm not a big baseball fan, but I know the game. My wife loves it. Home run hitters in Major League Baseball, they could hit home runs naturally. If you looked at Mark McGwire or Barry Bonds' home run statistics over a 20-year period, there was a natural variability in how many home runs they hit every year. But in the steroid era, there were more than the long too. So even on that natural cycle, there was a human influence, right? So that's how I but here is something that's important for anyone that's discussing climate change with your grandma or your staffer from the Senate or whomever to understand, because it's one of the most ill-posed, inaccurately described aspects of climate science that I face. And that is the notion that solar forcing or some of these other natural variabilities that we talk about are the primary drivers of our climate system. They're not. What has the largest red bar up there on all of these sort of forcing functions on climate? Greenhouse gases. Yes, the sun gets things going, it's the driver. Yes, things like aerosols and clouds and land use change affect reflectivity. But greenhouse gases, by a couple of orders of magnitude, are the dominant forcing in the climate recipe. I was somewhere the other day, And on the fly, I developed this analogy because it worked. But I was speaking to someone and they had some quiche. And that was one of the refreshments. And I said, what is the dominant ingredient in quiche? What is it? Egg. But when someone comes up to me and says, oh yeah, no, it's the sun cycle that's causing the climate change, that's like saying the onion in the quiche is the primary ingredient in a quiche recipe. No. Greenhouse gases are the eggs, right? But yet you see people focus on the minor contributors. And so it's important to understand that because I find, because let's face it, most people aren't climatologists, so they wouldn't necessarily know that. But it's important to know that radiative forcing is driven mostly by greenhouse gases.
When you point that out, have you ever changed anyone's mind?
Yes, because a lot of people, now,
Good.
yes,
There's hope.
but, you know, it's usually people, you know, there's a study by Yale Climate Communications Group called the Six Americas Study. If you haven't heard of that, go Google it. And it talks about that America breaks out into 6 different categories, percentage-wise. And there's one at the end called 10% dismissive. It ranges between 10 to 13%. You're not going to change their mind. There are some people that are just like, you know, they're just, but usually some that are kind of more in these sort of somewhat skeptical, but just because they don't understand range, you can reach. So, all right, let's move on. So it's the greenhouse gases, they're the sort of key contributor. We need the greenhouse effect. If we didn't have it, we couldn't live comfortably on the planet. Right? We'd be too cold. So greenhouse effect is important. We have to have it. The issue is we've got to keep it in balance and not get beyond sort of warming to a point of sensitivity. Well, how do we know, Marshall, that it is humans? That's a question I get often. Well, there are lots of different ways that we know now. One is that our climate models, believe it or not, are pretty good now. Some will try to say that they aren't, but they actually are. I mean, 10 or 20 years ago, they weren't as good. Now they're pretty good. And so when we run climate models with just natural forcing, that blue line, notice what we get. We don't reproduce the temperature change over the last several hundred decades, which is the black line, what's actually happening. So if we only run our climate models with just natural forcing, we don't reproduce what's happening. Only when we run it with human and natural forcing. And yes, there's variability. Yes, there are temporary cooling periods when a big volcano erupts because it spews sulfates into the stratosphere, and that is a reflect that blocks the sun. But the mean contribution suggests that humans are part of the reason we're seeing this amplified warming trend. I'm going to move on. So now let's kind of get into extreme events, because that's really kind of what we want to talk about today. The observed frequency, intensity, and duration of extreme events have been changing as the climate system is warmed. This is a fact, and our National Academy study showed that. It's been a controversial discussion. But there's strong interest because people, the public, presidents, Congress people, they recognize when extremes happen, not when averages change. It's the extremes that get attention. Drought, floods, heat waves. So, this is from IPCC. As we're changing this distribution, we're changing the frequency and intensity of extremes. Nobody's going to notice an average 2, 3. I mean, it's important. People always ask me, oh, that's 2 degrees of warming. What's the big deal? I was like, would you want your kid to run a 2-degree fever for 100 years? Body will start to respond to that in days. So you got to give a reference or context for people. So here's some projected changes in temperature. This is from the most recent IPCC using their RCP. These are just different scenario pathways that they use in the models. Assumptions, scenarios, that the past version they use scenarios, 18, etc. And the most aggressive scenario has the planet by 2180 warming up to 11 degrees Celsius. Convert that to Fahrenheit, really scary. But even some of our less aggressive RCPs, the years 2040, 2080, we're still up 2, 3, 4 degrees Celsius. Convert that to Fahrenheit, and you'll really see what that means. What about projected changes in precipitation? This is out in the year 2080. The real lesson here is places that are wet generally get more wet, and places that are dry out more. That's kind of always been the mantra. This is some data from NASA and also IPCC showing the frequency of drought increases. Now, interestingly enough, in our breadbasket region, there hasn't been much increase in drought. That's kind of a recent phenomenon. But if you look globally, and this is PDSI, is the Palmer Drought Severity Index. It's just sort of measure of drought. You can see a lot more red and yellow and orange than you see green and blue. All right. And if you look at trends in PDSI globally, clearly, and this is just up through the early 2000s, some older data, you can clearly, in fact, I'd like to kind of see that for up through the recent years, the last 10 or so years. I suspect that this will be like that.
And this is measured, not modeled data.
This is actual data. This is actual data. These are the actual changes in precipitation in the United States from 1901 to 2015. And this is all data courtesy of the U.S. Global Change Research Program, National Climate Assessment. And again, right now, the middle part of the country has actually been getting increased rainfall, right? Seeing tendencies towards drying out in the west, and we've certainly seen that in places like California. But look at the southeast, right? Sort of neutral to maybe, it's kind of neutral. I just call it neutral right now. Right now, we haven't seen heat change, but if you look carefully in the middle part of Georgia, there's this area of decline. Some parts of Appalachia and Carolinas. So it's a mixed story in the U.S. right now.
So this is just looking at one of the 1901 and 2015. Just two single years.
No. It's not looking at the endpoints. Right. It's kind of an average change over that period.
Okay, so the percentage change is relative to what period?
Good question. Relative to the sort of 20th century average. Now I want to focus on the wet side for a moment. This is a look at extreme one-day precipitation events in the contiguous 48 states from 1910 to 2015. There's some suggestion that, there's more than suggestion, that in recent decades, the heaviest rain events are heavier. So when it rains really hard, it's a heavier rain event than it was 50 years ago. And why this is really the kind of stuff I do most of my work on. And why I think we're seeing more urban flooding is because many of the urban stormwater management systems are designed for the 1950s rainstorms. The engineering was assumed to, the rainfall was assumed to be under the assumption of stationarity, that the 1950s rainstorms would look like 2017 rains, and they don't. And so this is a well-known problem in the civil engineering field, and they're working on it. But many cities' stormwater management is assumed to design and engineer to that assumption of stationarity. This is interesting and one that would just really cause problems to a climate scientist talking to a policymaker. This is the average drought conditions in the contiguous 48 states from 1895 to 2015. What would you say? What is the message that you get from that? It's variable, right? There's no real strong signal from that metric. Here's the last 15 years, U.S. land under drought conditions, right, from 2000 up to 2015. I guess I can say that I see a lot more exceptional drought in the latter years, but can I link that to climate? Can I link that to climate change? I wouldn't go out on a limb and say that just yet, just based on these last two figures. It would be irresponsible to say, yes, we're seeing more drought because of climate change, based on that. Now, there's some other things that I think we can say that perhaps, but I mean, I might be able to make the argument that the most extreme categories have become more frequent. And that would be consistent with what climate scientists expect. What about projections for the future? This is from the 2014 National Climate Assessment. All right. And again, for whatever reason, the National Climate Assessment used the old A2 scenario approach rather than the RCP. But it's just a different scenario. So under the most aggressive scenario in the models, you can see that Southeast is still kind of in that neutral range with perhaps in the fall some drying. But the breadbasket of the and parts of the Southwest, dry. These are projections. These are climate model projections. Now let's look at this from a food perspective. Here are corn, wheat, and soybean yields from 1866 to 2010, courtesy of FAS. And what you see is greatest gains in corn yields and global corn yields continue to increase, and there's less yields gains in wheat and soybean, and actually somewhat begin to flatline. I mean, this is things that people in the agricultural world understand. It's probably not planting any new flags anywhere. But the reason I show this, and let's make the point here, this is high U.S. producer prices. The point, look at the spike in 2007. If you look closely at 2012, you can see price spikes. And one of the drivers of these spikes is drought. Right? So it sort of makes the point that, remember we started this discussion talking about the hydroclimate influences on food supply and food production. So hydroclimatology is clearly a function of price. So are we causing the changes in climate, extreme events? Are we causing more heat waves, more floods, droughts? That was the point of this National Academy study. Why do I have a fertilizer and lawn in this picture? Because, again, it just kind of makes this point I made earlier about steroids. Grass grows naturally, but when you put fertilizer on it, it grows faster. So we can influence natural cycles. So what factors influence extreme events? Definitely natural change. Have you noticed that I have always in this talk talked about the natural variability in the climate system? We don't forget that. There's large-scale circulation, there are internal modes, El Niños, PDOs, there's specific weather patterns. This tornadic event that we just saw here in Georgia devastated Albany, bad tornado. That was a very significant weather pattern. It didn't have anything to do with climate change. There'll be some that will try to make that leap. As you'll see in a moment, we can't make that leap. But we know that even with this natural variability, there is climate change, there are anthropogenic forcing on top of that. So believe it or not, we presented this to Congress. I was a part of the rollout team that went up to Congress in April and presented this new National Academy's report. And the point we were trying to make with this simple graphic, because we figured they like cookies, is that if you slightly change a particular ingredient, you're going to get a slightly different chocolate chip cookie. If you put more melted butter, you're going to get a slightly different cookie than if you put all white sugar. And this is the same thing with an extreme event in the atmospheric system. Slightly different atmospheric conditions will produce a slightly different drought or flood or heat wave. And that will depend on the sequence of natural processes, whether we're in an El Nino or not. We all know here in the Southeast that whether we're in an El Nino or La Nina determines some things about our rainfall patterns in the Southeast, particularly in Georgia. There are linkages through what we call teleconnection patterns. So that's whether we're in a La Nina is one cookie, whether we're in an El Nino is another cookie as it relates to the type of precipitation we have that following fall. So we know that there's variability, but the challenge for this new branch of climate science called attribution is how can we evaluate the relative contributions of multiple causal factors to the change? In other words, there's a new science that's out there that tries to say how much of an extreme event was related to natural processes versus anthropogenic change. This is the field of attribution. We're in it. It's here. If you think back to the big floods in Louisiana this past summer, there's a study that came out and suggested that flood had a 40% contribution from anthropogenic forcing to the climate. In other words, without climate change, there was a chance that it might not have been as pretty significant. So extreme event attribution is studies that calculate how much human-induced climate change or other factors has affected an individual event's magnitude and probability of occurrence. And the reason that the National Academy of Sciences called for this expert of 10 of us to come together and really write this report, a 160-page report, it's available out there, just Google extreme event attribution in National Academies. It's a free download if you download it from your EGA computer. Is that it was kind of a wild, wild west the last 5 or 10 years. There were no guidelines, there was no assessment. People were just kind of, oh, Sandy, they'll go do a study on Hurricane Sandy, and there was no sort of, it was just a wild, wild west. There was no kind of order to it. So that was the whole point of our paper. And yes, attribution of extreme events to anthropogenic change may be complicated by low frequency natural variability. That just means things like PDOs, Atlantic oscillations, ENSO cycles. But we also know that there's human contribution as well. And what we found, this is kind of the bottom line, is that there is greater scientific confidence for certain extreme events being linked to climate change than others. And this is important. There are some things that we know right now have stronger attribution to climate change than others. And those are the events that are linked to temperature. So there's pretty good evidence that extreme heat waves that we're seeing have a link to climate change. There's pretty good evidence that the lack of or the reduction that we're seeing in cold events or cold records is related to climate change. There's pretty decent evidence that hydrological drought and heavy precipitation events are linked to climate change. There's less confidence in linking severe convective storms, tornadoes, for example, and hurricanes and extratropical cyclones. So if you look at it the way we presented it in the report, anything down in here, there's less confidence. Anything up here, there's more confidence in their linkages to climate change. So extreme heat events, lack of cold, drought, rain, extreme heat rain. Tropical cyclones and snow, kind of in the mid category. Now, the point to take away from this is that doesn't mean that we won't eventually learn that these are strongly linked to climate change too. We just don't have enough evidence to say it right now. But we have a lot more evidence to say with more confidence that these things are. Another thing that we kind of really pushed in this report is that we got to get rid of this question. We've got to get rid of that question. Was that event caused by climate change? So whenever there's a drought or whenever there's a big hurricane, we've got to get rid of that question. The media always asks it, people always ask, oh, was that drought caused by climate change? That's the wrong question because of our cookie example, because there's always natural variability in the mix. But what we have to ask is, are events of this severity becoming more or less likely because of climate change, or to what extent was the storm or drought more or less intense because of climate change? So we have to erode this question. We have to get rid of that question. All right, so let me shift gears to now the last part of the talk and talk about some ongoing work in our group here at UGA related to this whole notion of hydroclimate. And some of you who've seen my talks before, perhaps seen this before, because this is from a paper that my PhD student, Benita Casey, who's now a postdoc at Oak Ridge National Lab, published along with Cassandra Johnson at US Forest Service and myself. And it's also related to some work that we published last year as well. This is a climate change vulnerability index that we developed for the state of Georgia. And how we developed this index is that we pulled together using a database called SHELDUS. SHELDUS is a hazards database that's composed of floods, drought, and heat. We pulled together data from temperature records and precipitation records, social vulnerability index, how many people of certain economic status, racial makeup, their ability to get to hospitals, how many homes have air conditioning. These metrics of social vulnerability were in there. We had in there, actually, we used some land use data. Liz has been working with the to try to assess how much of a county is urbanized. And we also used FEMA data on flooding, areas that are prone to low-lying flooding. And through the magic of science, we pulled that together into a vulnerability index. And you can read about it in the paper, right, how we really did it. And what we found is that there are a couple of things. Georgia, from the 80s to the 2010s, have become more climate vulnerable in general. Because if you notice, it went from being more yellow to a lot more orange and red in general. But there are some counties that have popped out as increasingly vulnerable. The urban counties, if you notice, have become increasingly vulnerable, mostly because of extreme heat and flooding. But the counties down in here in the Southwest and these parts is because of drought. Because if you look at how she did her analysis, a lot of those counties depend on agricultural activity and productivity and jobs. And so you see more vulnerability light up in some of these counties. Now, of course, these counties along the coast are lighting up more because of increased flooding. Athens lights up is particularly vulnerable just because the county has such a large socially vulnerable population. It's not that there's any particular thing that's driving it from a weather climate change. So I invite you to take a look at that study if you're interested. We've got some more recent work that was funded by NASA on the food, energy, water, where we're looking at a couple of research questions. Can precipitation metrics such as precipitation per capita or precipitation per acre be used to quantify sort of precipitation availability for places using NASA data sets, primarily satellite? If so, can spatiotemporal trends in these metrics be useful in the assessment of the energy, water, food nexus capacities and vulnerabilities in places? And then how will the addition of urban agriculture and irrigation affect urban microclimates? That's kind of getting into things we've always done. Then how vulnerable is urban agriculture to hydroclimate variability and extreme events? So these were sort of the primary research questions we posed for that project. And it was motivated just by this little graphic that I made. There's no cause-effect relationship in this. I just was looking at this map of urban lights one day around the US, and I said, gee, we already know that people like settle where there's water, right? But I just looked at this and then I plotted sort of rainfall from the GLDS, which is Global Land Data Assimilation System. And I was like, yeah, people usually are where there's water. I mean, you can again, there's no cause-effect relationship here, but you can see where most of the urbanized population is. You can see that's generally the wetter part of the US and then again out here. So that was what motivated that entire study. So just to give you an example, we have a satellite up there now called the Global Precipitation Measurement, GPM. It can measure rainfall from space globally. So here's global mean annual precipitation from one of the instruments on that satellite. We do some math to couple that with global population density data to produce this metric we call precipitation per person in tons per year per person. Now look, precipitation isn't the only story when we talk about water supply, but we are interested in just the precipitation aspects because even with this type of metric in places perhaps that are not as well instrumented as the US, it can tell us some things about water stress and scarcity. If you sort of aggregate that over a country level, you can begin to see which countries have the greatest average precipitation per person. Now, it's interesting then, for example, Egypt pops out as fairly low precipitation. I mean, that makes sense to some degree. Look at India, right? Because remember, this is precipitation and population in there. So you think about it from this perspective here. Precipitation per person for different countries on the top, total population per country on the bottom. If you kind of just sit with data like this for a while, you can start to think through why some of these countries perhaps are lower or higher than other countries. All right. So yeah, that's kind of neat that we can do those kind of things, but what we're really trying to do is develop these metrics so that we can assess the potential for precipitation-driven food production and other ecosystem services in cities and how those vary. That's kind of the goal. So that you can see our framework there. And can we use these metrics in that water-based vulnerability assessment? So I'll give you an example of what I'm talking about. Water from 1 inch of rainfall. Here's a table that shows how much water you get, area and amount from 1 inch of rainfall for different places. So for example, if Atlanta receives 106 billion gallons of water via rainfall in an average year, if the per capita water use is 40,000 gallons per year, perhaps it's clear that a large percentage of the population could be sustained from just sustained rainfall, right? Assuming no evaporation. So again, we're making some very, perhaps unrealistic assumptions. But residents of urban areas in less developed countries, which are often densely packed, have limited access to potable water. And that's a publication from one of my co-investigators on this. So one of the things we've been using these metrics for is to assess the potential for ecosystem services such as urban rainwater harvesting and other concepts. So my colleague from University of Utah, Steve Burrian, and his graduate student Stout, they assessed that 35 gallons, for example, of water per person are required in Delhi, Kolkata, and Bangalore, and that rainwater harvesting could provide roughly 20% of the indoor water demand. And we established that by using some of these precipitation metrics that we've developed, because in India and some of these other countries we've looked at, they don't have very dense rainfall data in their sort of social population units. So we can use satellite data. And so this is work that just, we're only in year one of this grant, by the way. So this is kind of work that's ongoing in this area. All right, so final slide. This is just the slide that I end with to kind of talk more about the communication. And I mean, this is just something that I love, and I saw Steve McNulty from the US Forest Service present it here, probably at UGA a few years ago. And you know, he showed this graphic. Actually, I don't think he did. I think I wouldn't have found this. Because farmers tend to trend skeptical on climate change in some studies. So Steve was talking about, he deals with a lot of foresters and others that also skew skeptical. So he just talked about that he kind of uses this E.L.F.L.A.N.D approach when he's talking to stakeholders and practitioners that skew skeptical. And he cautioned that when you're talking to skeptical groups, you have to establish contact with those groups. In other words, don't go blazing in with your PhD or your big fancy academic credentials and say, I know more than you, even though you live here on your farm every day. Because that farmer may say, well, at my farm, it's cool. It's been cooling the last, and that could be the case. And, you know, unfortunately, a lot of people tend to sort of ascribe what's happening in their local community, what's happening globally. You know, everything's local to them, right? And that's just, you know, we have to understand that. But by establishing contact and listening to them, yeah, well, yes, ma'am, your farm is cooler the last several years. But can you tell me whether you've noticed that there's been more drought here in Albany or whatever? And you start having that dialogue, and they might come out and say, yeah, you know, there has seemed to, and it's been, and you'll start having that conversation, you establish that, and you find common ground, and then you lessen mistrust, and then from there you can start to assess needs and work and move together. And that's kind of the approach I've always used, but he actually gave it a name, because I always tried to identify the value system. So if I'm talking to a group of Republicans, right, or conservatives, put it that way, you know, I start talking about how national security is that's a value I know that is important. I was talking to a group of staffers from our congressional delegation here in Georgia. I gave a talk and I was showing the California drought. One of them asked me, well, why do Georgians care about the drought in California? I said, do Georgians go to Subway and get a sandwich? Or are you going to have a salad tonight? Because probably something in that salad or on that Subway sandwich is grown in California. And when there's drought in California, that drives up price. I said, but watch what I did to kind of really pique his value interest. I said, but guess what? Why aren't Georgians growing? Why is it that California grows 90% of strawberry or whatever, or 75% of lettuce? Why can't Georgia? So you start tapping into their value chain, and then you lessen that mistrust and that immediate wall that often is put up when you're speaking to people who may a priori come in with a different perspective. So I wanted to end with that, because as we go forward in all of our activity as it relates to food, water, energy, and climate, we're going to have to strategically think about how we present that information. Thank you. Definitely take some questions.